we now want to look at numerical integration. And the way we're going to introduce this topic is by integrating a well-known function, the square of sine of x. And as a matter of fact, I need to change this notation to t, since t is my independent variable here. And so why am I deviating from the typical xy variables that I've been using so far in these tutorials? Well, so if you remember, okay, this is the definition of velocity, right? The derivative of position with respect to time. So if I integrate both sides with respect to time, then what I get is the total displacement for my motion. Okay? The integral under a velocity versus time function integrated over time is going to give me the total displacement. So here I am using v and t as my independent variable, v as my dependent variable, and the total displacement delta x is what we are wanting to calculate. Now, how does numerical integration work when you have a discrete set of points that supposedly lie along a function, but the discrete points have a finite width? They're not infinitesimally small. Okay, well, the integral, of course, represents the area. And so one way to do it is to look at your first point and draw a horizontal line to your second point, and then draw these shapes. One is going to be a square, and the other is a triangle, and you add up these two areas, and that gives you your first approximation. And then you do the same thing for the next two data points. Add up the rectangle and the triangle, and then you do the next for the next two data points, and you add up the rectangle and you add up the triangle, and then you add everything up, and sooner or later you're going to get an approximation for the entire area under the whole curve between your limits, whatever your limits may be, right? So if I start my stopwatch here and I end my stopwatch here, and I track the velocity of my object and it falls along this trend, I can keep drawing these rectangles and triangles, and I can keep trying to calculate these, right? Now, so that's not bad. That's a decent approximation when you're in a pinch. But there are some more sophisticated values that take into account some of the rounding errors that occur when you use this method. So we're not going to go into the details of how to derive the method or where it comes from, but we're going to use a method that is called Simpson's method. Okay, we're going to employ a method called Simpson's method. And the algorithm for Simpson's method is this. Okay, it looks like this. So if I have n points, okay, if I have n total points, then I'm going to do an iterative loop, much like I did for the derivative, except it's going to look like this. So you look at whatever I value you are looking at, whatever index value you're looking at. You look at the 2 times I minus 1. So if you are at the say the fifth ith element, okay, then the fifth ith element, okay, 2i would be the 10th element, and then subtract 1, so the 9th element. So you look at the 9th element, and then you multiply that by 4 times the 10th element, and then plus the 11th element. Okay, so you don't run this over your entire data set, right? You're not going to calculate n unique values for x and then sum them up. You're actually going to calculate n minus 1 over 2 unique values for x, and then you sum those up. And then you multiply the sum by your delta t increment, or the distance between each t value, divided by 3. So you run through this loop, this algorithm, for each element in n minus 1 over 2 times. Then you sum all of those up, and then you multiply that by the time increment divided by 3. So once again, we're not going to explain where this comes from. We're not going to take the time to do that, but this is called the Simpson method. Okay, this is known as Simpson's rule. And so with that in mind, let's come back to our function here. And so what I need to do first, okay, what I need to do first. So I've already defined my function. And the next thing I need to do is define n. Okay, so let's let n equal the length of t, right? So that is the length of our time array. And by the way, this method works best when you have equally spaced time increments. If your time increments are not equally spaced, this method suffers. But there are more sophisticated methods one can use, and there are simpler methods one can use. The Simpson's rule turns out to be a very good balance between the two. So if you don't need too much sophistication, you don't need something that is extremely sophisticated, and you want something to run fairly efficiently, then this method is a really good one to do. So we're going to define our the number of our endpoints first. And my personal notation is the value on the summation. So the n minus 1 over 2, I typically will define that by the lowercase n. So if we do that, then we will get this. And what we're going to do, all right, is I'm also going to show you a new piece of syntax, and that is this. Okay, that is this. We're going to define lowercase n to be n minus 1 divided by 2, but I need this to be an integer, right? Because I is going to be discrete integer values. And so I'm going to define this to be an int. Okay? Int n minus 1 divided by 2. And that will make sure that this is an integer value. So this shouldn't complain, and it is. Maybe I don't need the NP there. Let's see. Yeah, no, I don't need the NP there. So this defines the integer value. And then the next thing I need to do is define an array for my results. Okay. And so our results are going to be displacement. So I'm going to label this as X. And I'm going to say np.zeros. And there's going to be n of them. I'm going to run my loop n times. So now we're actually going to do the calculation for I in range, lowercase n. And so, once again, this is going to be, whoops, the velocity at the 2 times I minus 1 index plus the 4 times the 2i index of velocity plus the 2i plus 1 index of velocity. Okay. And so our loop is going to look like this. Xi is going to equal v2i minus 1 plus 4 times v to the 2i, and I technically need multiplication signs in here or else it won't know what to do. Plus v of 2 times I plus 1, right? And I'm actually going to space these out via spaces just so I can see each term a little more clearly. Okay? And so now we're done with the loop. And once again, okay, I run my program. It's not complaining at me. That's good. It doesn't mean I didn't make a mistake, but it does mean I did not make a syntax mistake that Python caught. So now my total displacement, I don't care what we label this, we can label it xtot for total displacement, is going to equal the sum of x, okay? And I need to multiply that by delta t divided by 3. So what I'm going to do is also define delta t. And delta t is going to be the time interval between each of my spacings, time measurements. So this is going to be t1 minus t0. And each of my time spacings are going to be equal to that since I'm dividing this range from 0 to pi up into 10 equal pieces. So I'm going to take delta t divided by 3, multiply that by the sum of our loop. And before we print this, before we run the program, let's see what the answer ought to be. Okay, so if I actually do this integral, and this is why I did this integral, because this one has a known solution. So if we do this integral, we should get a number close to 1.57. Okay, we should get something close to pi over 2. So let's run and see what we get. Okay, 1.468, right? 1.468. Not terrible. And the difference between the absolute solution and our solution is that we are only taking 10 discrete data points, okay, as opposed to infinitely many data points, assuming the function was continuous. But notice what happens, okay, as I approach that value. If I keep increasing this by a factor of 10, what happens if I split my interval up into 100 data points? Ooh, okay, so now it overshot. Not by much. Actually, it didn't overshoot. It slightly undershot. 1.5708, and we got 1.5707. Now, 1/10,000th or one part out of 10,000 would usually be very good. Okay, we would call that a success. But because computers can crank these out to nearly arbitrary precision, okay, you'll see how you saw how fast that ran 1,000 data points. And so if I run it with 10,000 data points, it doesn't hardly take any time at all. So unless there's a limit to something, and we can even do 1,000,000 data points, and it still won't take terribly long. It might take a couple seconds here, but it just cranked out 1,000,000 data points, right? And you can see that 1.507963, if we include more digits here for Wolfram to display for us, we might actually see that we are, within maybe 1 out of several million parts in accuracy. I'm not sure what is taking so long here. If we simply do this, and let's just take pi divided by 2. Okay. Okay, so might be hard to see. So we'll zoom in here. 1.570796. Whoops. 1.570796 326 79 49 48. Okay, so we are out to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13th decimal place before our result doesn't even match exactly with the numerical value of pi divided by 2. So if we, go back down to say 10,000 data points here, we are still running within well below 1 out of 1, 2, 3, 4, 5, 6, 3, 2, 6. Yeah, 3, 2, 6, 7, 9. 3, 2, 6, 7. So this decimal place, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. we're sitting at 1/10th, 1,000th, 1,000,000th, 1,000,000,000th, 100 billion. 9 out of 100 billion places. Okay, so that is by far more than enough precision for almost any application you would need it for. Okay, so if you know what your function is, you know what your function needs to be, and you can evenly distribute your t-values, then this is an absolutely powerful method that allows for a very speedy calculation as well as a very accurate calculation. Pardon me. So this is a simple way to start doing numerical integration. Now, there are more sophisticated techniques. I cannot stress that enough. One technique worth mentioning is called the Monte Carlo technique, but if you run a Monte Carlo integration, it will not look anything like what's on your screen, because it actually relies on statistics, and you would have to program it a completely different way. But that would be in cases where you don't have any other options. If your function is absolutely not analytical, or it is put in a very weird form, you may need to do a Monte Carlo solution. But note also, okay, this particular method here, as long as you have equally spaced independent variable data, it won't matter what you put here. Now, this is obviously a function, but you could put an array of measured values. Okay, so if you have experimental values that you can put into an array, you can put those values there, and you can use this method to get an estimate for the integral. Where would you do that in? You probably wouldn't do that with times, velocities, and displacements, but you might do it with displacements and forces and work, right? Remember that work is the integral of f dx, right? So if you have a variable force acting on a particle and makes it move, then the work done is going to be the integral of that function. So if you have force data and position data, then you can integrate that, and you can get a value for the total amount of work that was performed on the object. Okay, but this is the meat of the program right here. Okay, this is the meat of the program. It is this algorithm that is doing the machine heavy lifting. Okay, it's doing the heavy lifting. And if you want to know more about where this derivation comes from, then you can feel free to talk to me, and we can walk through that. But just know that this is not the only one. There are others out there, but this is a very powerful one, and for most applications, maybe the only one you need. So it's very simple, but it is extremely powerful. So before we go, let's do one more example. Okay, so I want to do a bit more of an exotic example, and let's say np cos x squared times np dot square root of 1 minus np dot cos x. Okay, so this is a rather complex function, but it looks like this. Okay, it looks like this. And so we're going to integrate again from 0 to pi. And the reason I like this example is because it does have an analytic solution. 7 times 2 to the 3 halves, all divided by 15. Now, the analytic solution is 1.3199326 when you put it in a decimal form. Okay. And if I, again, back this down to just 10 data points, what happens? Does it give us... whoops, that's because I need these to be t's. So let's see. Okay, so 0.64, not real close to 1.3, actually almost half off, right? Almost half off. But if I increase to 100, what happens now? Ooh, 1.24. So the lesson here is, over your interval, you need to have fairly small intervals in between your points, or else the rounding errors when the algorithm, it's not Python's fault, it's a limitation of Simpson's rule. When you have large delta t's, there's going to be a lot of rounding errors in the way it calculates the rectangles and triangles. But as you increase in these values, those rounding errors go away pretty quickly. And as you can see, with 1,000 data points, we're already getting very close. So 1.3199, 1.3125, we're already within the 7 out of 1,000 range, 7 parts in 1,000. And if we do 10,000, now we're going to be in the 1 out of 10,000 range, or about 8 out of 10,000 range, 7 out of 10,000 range. And again, if I go up to 1,000,000, then this should be fairly accurate. Yep, 3.19925, 9932. So we're still off here. This particular function doesn't converge quite as fast as the sine squared function did with 1,000,000, but this is still accurate enough out to the 5th decimal place, which is hundreds of thousands, or tens of thousands, right? No, hundreds of thousands. Yeah. So we're accurate out to hundreds of thousands, which is usually more than enough. It's absolutely sufficient. But there's, as long as you're willing to let your computer sit here and run, you can keep adding these zeros. Now, after a while, it will take some time for the computer to chug through these. Okay. So I'm at 100 million now, and it will probably take the computer some time to do this. But I'm going to go ahead and sign off while the computer is working. And if you guys have any questions, drop them in the comments, and we will see you in the next tutorial.